I know that my nice picture was erased. But we have this. You have silver ions, or you have chloride ions, and then you have this pile of precipitate on the bottom of the container. The formation of this precipitate releases energy. What would the water experience?
Wouldn't that be like hydrogen ions and chloride ions, the ones that are floating?
Well, the hydrogens are spectators, because the chloride came from hydrochloric acid, so there are hydrogen ions present. And the silver came from silver nitrate, so there's nitrate ions present too. But the hydrogen ions and the nitrate ions don't do anything. They're just there, so they're spectators. I didn't even put them in. The only thing that we observe is the formation of a precipitate. So you get this white solid that falls to the bottom of the container, and that's all we can see. So even though the hydrogen is there, and a lot of times hydrogen does stuff, but when they're just hydrogen and nitrate, that's a strong acid, so they just stay apart and don't do anything.
Won't you experience a gain in temperature?
What will?
The water.
The what?
The water.
Oh gosh. The water does. So how much water do we have?
Yeah. Oh.
You know, we're probably going to have to use Q equals MC delta T, right? So, yeah, we have this reaction that happens. How much water do we have?
100 ml.
When you combine these two, there's 50 ml of one solution combined with 50 ml of a different solution. So the volume is 100 ml. What then is the mass of water?
100 grams.
Is it close enough
Yeah, that's
to 100 grams to consider it to be 100 grams?
Yeah.
In the 50 ml of this silver nitrate solution, is that exactly 50 ml of water?
No.
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 It's 50.0 ml of the solution. Isn't some of the volume, though, the silver ions and the nitrate ions, doesn't that contribute to some volume? Yeah, a lot, though.
No.
Turns out that it's not very much volume at all. So when you have a solution, I want you to assume, unless the problem tells you otherwise, it's safe to assume that the volume of the solution is the same as the volume of the water that the stuff is dissolved. All right, what is the problem asking us to do? The two solutions are initially at both at 22.6. And as this reaction occurs, the temperature of the water is raised to 23.4. So what do you know for sure about this reaction?
The change in the temperature.
Know about the reaction. Tell me, is it exothermic or endothermic?
Exo.
It's exothermic because it's giving heat to the surroundings, which is the water. So the reaction is losing. If we calculate delta H, what will it be? Bonds are forming. That's right. They were separated, now they're coming together. It should give off heat, and sure enough, it does. Delta H should be negative. So we agreed that the mass of the water is 100.0 grams of water. And we're going to have to use this relationship. Thermodynamics says that Q gained by the water, because the water is the one that rose in temperature, it gained heat, equals negative Q lost by the reaction. This is what's losing heat. Okay, so the Q gained is water. So Q of the water equals what? It's equal to mass times C times delta T. You can always find Q for the water if you know how much you had, because you'll have the temperature at the beginning, temperature at the end. So you'll probably be able to find the Q for the water. Okay, well, what is it? It's 100.0 grams times the specific heat of water. Anybody remember it?
4.18.
4.18.
4.18.
I remember somehow. I don't know.
Write that down if you did not know that or remember it. Water's specific heat capacity is 4.18. I'm sure it's in the book, but just to save yourself the trouble. And you'll remember, you use that number a lot, it will stick. Yeah.
So about the other, like, oh my gosh, the specific heat for the other gases. Do we need to know?
Other things, you don't have to memorize them. You don't even have to memorize water. I'll give you that. They'll be given to you. I think there's a table in the book. Does anybody remember reading through the book and seeing a table?
No, reading the book. That's a joke.
All right, I know how that sounded. Times delta T. I don't have the delta T in here yet. 0.80. Where did I get that from?
Subtracting the two.
Yeah, that's the change in the temperature. It's the final minus the initial temperature is 0.80 degrees Celsius. So multiply all this out, and that will allow us to find the Q for the water. How much energy did the water gain when it rose in temperature? Anybody got it?
328.
2 sig figs,
So 320.
330.
positive. How do you know that Q is positive for the water?
Oh, because it gained it.
It gained heat, and mathematically, how do you know that?
There aren't any negatives.
There's no negatives in there.
So
Yes?
There is no reason.
Because it's like ML is equal to radius.
Yeah, because the density of water is 1.
Oh.
That is an approximation, but it's pretty close, so we're just going to go ahead and approximate. Okay? So assume that the density of water is always 1. If you know the volume of water, then you know the mass of it, yeah.
So if you had it in like some weird other solute or whatever, then you
Yeah, it's going to be in water every time, Lena, though. Seriously, you'll always have water.
Okay.
It will be. Yep. What if water's temperature went down? Then that number would be negative, wouldn't it?
Yeah.
Final minus initial would give you a negative number, and so your Q is going to be negative. And that's fine, because remember, Q is a flow of heat. It tells you whether heat is going in or going out. So for the water, heat was going into the water, so its Q is positive. Yes? What does that mean about the reaction?
It releases
How much?
energy. 330.
So Q of the reaction, anybody have a different name for Q of the reaction before I put a number on it?
Oh, gained.
Greek letter.
Oh,
Delta,
Delta.
another name for a Q of a reaction. Amount of heat in a reaction, delta H. Delta H. Delta H is a Q of the reaction.
You mean triangulate?
Yeah, that's what I mean.
Alpha
So
beta.
Q of the reaction, which is delta H. Because of this thing right here, this rules calorimetry. That's why we do calorimetry, is because of that. Don't leave that out. That's the backbone of calorimetry. Negative 330 kilojoules. Not joules.
That makes me feel bad.
Negative 330 joules was the reaction. So if the water gained 330 joules, from where? From this reaction. Is that the answer that the question asks us for? Keep reading. Calculate the heat that accompanies this reaction in kilojoules per mole of silver
Oh,
chloride.
so that's like one.
This was not for 1 mole, was it? How many moles was it for? Oh, we have to do the math on that. Yeah, it takes stoichiometry. We want to know the moles of this thing right here. Well, I know how many moles of this and this reacted. How many?
Well, you don't.
Divide
gotta
the
do
mole.
that. So
Multiply those to get
0.05 liters times 0.1 molarity is 0.005 moles. Yeah?
Yeah.
Yeah.
Chloride ion, same thing. You have 50 ml of 0.1, so that's also 0.005 moles. So how many moles of silver chloride? Don't tell me 0.01.
0.005.
Right, it's a
moles.
1-to-1 ratio. We're not adding here, we're taking ratios. It's 0.005 moles of silver chloride.
Yay.
So why do we need to know like the CL?
To know which one was the limiting reactant, and it turns out neither one was, so both of them get used up to make the 0.005 moles of AgC.
Never heard of it. Always a limit.
So.
No, not this time. Not this time. Okay, so what is the answer, Then the delta H of this reaction is what? 330 kilojoules was the delta H for 0.005 moles that was produced.
330 times 0.00.
Oh my God.
Divided by 0.00.
Thank you. Negative 330 joules. Oh, we have to change the kilojoules. That's easy
Yeah,
though.
I knew that.
Small
Like, that's what
divide by
I
1,000.
Negative 0.33 kilojoules over 0.005 moles. And that's equal to negative 66 kilojoules per mole. So that means if a mole of silver chloride were to be formed, it would give off 66 kilojoules.
You know, if that was on the
That was
multiple
beautiful.
choice,
So good.
if that was on the multiple choice, I'd get that answer and then I'll just divide wrong because I don't have a calculator. I'd probably go like -1 million.
Yeah.
If you have this and you're trying to calculate this, take that denominator and there's a couple things you can do. Put it into scientific notation or take the denominator and make it a fraction. Because that would be, I'll do it over here.
The one.
You've got 0.33 over 5 thousandths. and take the denominator, take the reciprocal of it, and multiply it by the numerator.
that's
So it's
330
0.33 times
over
1,000
5.
divided by 5.
Why does
It's 330 over 5.
So it's 330 over 5.
Stop it.
Can you do that?
Totally.
Sure.
Oh my gosh.
That's
300 divided by 5 is 60, and then 30 divided by 5 is 6.
I can do that.
66. And scientific notation will work too. You don't like the scientific notation?
negative sign.
Yeah, you have the negative sign.
The negative sign. I'm like, what?
Why don't we just
Yeah,
divide the 1,000
it
by
is
5?
negative. So what? This is 3.3 times 10 to the negative first divided by 5 times 10 to the negative third. Right? What's 3.3 divided by 5?
How would we know?
3 over 5?
6.
3/5. 0.6.
So 0.66.
Right, Lena? Times 10 to the negative 1 minus negative 3 is second power. So that's about 60, which you'd find 66 in one of your multiple choice answers. Yeah.
So when you do that reaction over there, when you get negative 330 joules, that's for the 0.005 moles, and then you have to divide it by the 0.005 to get it.
Yeah, to get kilojoules per mole.
Wait.
Why?
Because why can't it just be one for like 2 times?
Oh, yes. That's what's difficult about this course in general, isn't it? The problems have so many steps that you're doing. The concepts are pretty much the same. You learned this last year. We're not using anything you didn't learn last year, but we have more steps involved, don't we?
And we have, I don't remember. It's not the math. It's
And
just,
yeah.
it's just the dividing.
You did calorimetry last year too.
No calculator.
Okay, so if the negative 330 was for 0.005,
We're gonna divide decimals.
when you did MCAT, could you turn the 100 down so that it was for 0.005 moles and then do it?
No, because we didn't know the specific heat of the reaction. So you have to use all the variables for water only when you do this MC delta T.
Oh,
And then, because of this thing, it's easy to find Q of water using MC delta T. You can't use MC delta T for any reaction, ever. So you got to find Q for the water. That's why calorimetry is so handy, because you do a reaction in water, find out what happened with the heat in the water, and then just change the sign on it. That's the delta H for the reaction. Okay? No MCAT for reactions, ever. We only have a couple minutes left, literally 2 minutes left. I want to at least throw Hess's law out. Not throw it away in the garbage, but throw it out to you.
Into our young little untainted minds.
Hess's law says this, that when you add reactions together, you'll have a resulting reaction. You could just add the delta H's together and you'll get the resulting reactions delta H too. Do you remember adding half reactions together when you balance redox reactions?
Oh, that was a pain.
No, it wasn't. It was fun.
I thought you were talking about something else. Yeah, that was totally fun.
You're talking a lot.
I am.
Does everybody else remember adding the reactions together when you did the half reaction method?
I actually liked
And
it.
get it overall. Sometimes you can cancel things out.
Yeah, I liked it.
Thank you, Sarabi.
It was okay.
Nobody else?
It was
loved it.
okay.
I took it home and married it. That's how much I loved
No.
Don't write this down because you won't have time. I just want to show you this and then we'll write it down tomorrow. This reaction, nitrogen plus 2 oxygens yields 2 NO2. This is a normal chemical reaction, and this is the equation for the reaction. But I need to tell you this reaction happens in 2 steps. Don't write it down, just look. The 2 steps go like this. The nitrogen and one of the oxygens combine to make nitrogen monoxide. And then immediately, the nitrogen monoxide that's made grabs another oxygen, and they join together to make 2 nitrogen dioxides. If we add these 2 together, what will you get? The nitrogen monoxide is made in one step and then gets used up in the next step. So when I add these 2 reactions together,
And plus O2.
these will just cancel out. Because I'll never see the NO because it was used up in the next step of the reaction. So I would just find this as my overall reaction, which is this.
Oh.
This plus this would give us the delta H of this overall reaction. That's what Hess's law says. Just like do the redox balancing.
No, that's so much easier.
Wait, so
I love doing Hess's law.